Alright, so let's do a quick example. So say I have two vectors, A and B, and A is given by 3i plus 3j, and B is given by 4i minus j. Now, from this example here that we saw before, all we have to do to compute the dot product A dot B is multiply the components together and then add them. So it's going to look like this. It's going to be 3 times 4 plus 3 times negative 1, which is going to be 12 minus 3, which equals 9. So the dot product of A and B here is simply 9. So now let's look at an actual physics example. So I have a sledder on a hill, and the hill's incline is a 10-degree angle. And we know that the mass of the skier is 70 kilograms. We know the initial speed is 2 meters per second. And we know the displacement is 50 meters. The question that we want to answer here is how fast is the guy going at the bottom. So in this case we're going to just assume no friction because we don't want to muddy the water here. And so to figure out how fast this sledder is going at the bottom, we need to figure out how much work is done by gravity. So remember, when we want to look at the work done by gravity, we have to figure out the work, or excuse me, the component of gravity that's going down the hill. And so in that case, if this angle here is 10, and this angle, the normal and the displacement, they're perpendicular just by definition, because the normal is always perpendicular to a surface and the displacement here is along the surface. That means that the angle here, so suppose I call this angle theta, this angle is going to be alpha, and alpha in this case would be equal to 80 degrees, and that's going to be the angle between the work force, which is the weight, and the displacement, delta r. Alright, so now, that being said, work is going to be Fg, or weight. Let's call it weight to be consistent. Excuse me, guys. Weight times delta r times the cosine of alpha in this case, because I defined it as a different angle, even though before we were defining it as theta. These definitions are just arbitrary. It just depends on what you want to call them, so that's why I've changed it here, because we have two angles to talk about. So figure out the weight. It's the same as always, 70 kilograms times 9.8 meters per second squared. Okay, and to that we multiply 50 meters, which is the displacement, times the cosine of 80 degrees. Okay, and remember, work is also energy, so the unit on this is going to be joules. So we're going to get 5960 when you crank that out in your calculator. Now, to this we combine it with stuff we've been working on before, in class, which is talking about change in kinetic energy. That's going to be your K initial plus your work. Excuse me, that's your K final, not your change in kinetic energy. Okay. So all we need to do is say, okay, 1/2 mv final squared equals your initial kinetic energy, which is 1/2 mv naught squared, plus your work, which we just figured out was 5960 joules. Okay, now we're after this guy here, so we move some stuff around. Alright, so when you move all that stuff real quickly, what you're going to get is your V final is going to be equal to the square root of V naught squared plus 2 times the work, so 2 times 5960, but I'm just going to write work because I don't have space, over the mass. And when you plug all that stuff in, you're going to get 13 meters per second. Ooh, sorry about that. Still getting used to my pen.